Hello, and welcome back to Physics 123, Quantum Mechanics 1. So we are now on our last lesson for this chapter. So before we begin the last lesson for the chapter, let's first review what we have discussed so far. So in the previous chapters, we have generalized the statistical interpretation of the wave function. So we actually have discussed the momentum space wave function, the position space wave function, and the energy space wave function. So for instance, this familiar equation for the wave function that we have is can be thought of as a position space to energy space transformation of the wave function, where the energy space wave function is the combination of these linear combination coefficients and the exponential part. So that can be thought of as the energy space wave function. We also have a Fourier transformation from the momentum space wave function to the position space wave function given by this Fourier transformation. So for the last lesson, we will now try to generalize the wave function itself. So we have discussed about the generalized statistical interpretation of the wave function, the generalized uncertainty principle, and now for the last topic, we will be generalizing the concept of the wave function. So a wave function can be thought of as a wave vector, wave function, an eigenfunction, an eigenstate, but all of these concepts, wave vector, wave function, eigenfunction, eigenstate, eigenvector, all of this represent the state of a particle or a system of particles. So this state is actually independent of any coordinate system. So in general, we can write this as a ket vector, curly s, as a function of t. It's a ket vector. And these vectors are again independent of any coordinate system. In fact, if you try to place it in a coordinate system, you get the wave function of that in terms of that coordinate system. For example, if you try to get the components of this state wave function or state vector in position space, you will actually get the position space wave function, and you can do this by just getting the components of it in the position space. So you take the inner product of this with the eigenfunctions of position. Similarly, if you take the inner product of this state with the eigenfunctions of momentum, you will get the momentum space wave function. And lastly, if you take the inner product of this with the eigenstates of the energy operator, psi n, then you will get the energy space wave functions. So we can now then generalize our time-dependent Schrödinger equation. So this is now our generalized time-dependent Schrödinger equation. Take note, we just replaced our psi here. Originally, this is h as a function of psi. So the function of s here as a function of t originally is our psi as a function of x and t. And our time independent Schrödinger equation, on the other hand, can be written in this manner. So in the in the position space version of this s of n, the time independent wave functions are our stationary states. psi n. And we can also write now the time-dependent wave function S in terms of the time-independent wave functions S of n. So again, this is just a familiar form or equation. If you replace this by capital psi and you replace small s here by small psi. So this is now our general state. It's a linear combination of stationary states. We can get, again, the linear combination if we know the initial wave function. If we are given the initial wave function, the wave function at time is equal to 0, then we can get the linear combination coefficients by taking the inner product of the eigenfunctions and the initial wave function. So this is now, we are now using Dirac notation. This can actually be written in terms of integral form. Please review the previous lessons on that. So that is how we solve the linear combination coefficients. To solve for the time-independent wave functions S of n, we need to solve this time-independent Schrödinger equation. So when we try to solve this, function, you can actually transpose the matrices to the other side. So you will have h minus en, and since en are just values and h is a matrix, you cannot subtract a matrix with a number. So we will multiply the identity matrix with our energy eigenvalues here, Sn, and this is equal to 0. So since the wave function cannot be equal to, the time-independent wave function cannot be equal to 0, then this must be equal to 0. And since this is a matrix difference, then in order for this to be 0, its determinant must be 0. And this is what we call the characteristic equation, because this equation is characteristic to the Hamiltonian and energy levels of your system. So you get the determinant, the absolute value sign in a matrix indicates determinant. So it indicates the determinant of the matrix. So recall your matrix multiplication, recall how to solve for the determinant of a matrix. So you have actually encountered finding the determinant of a matrix before when you try to take the cross product of two vectors. Okay. So the Hamiltonian in general is a Hermitian matrix. So it's a square matrix, an n by n matrix, and n, the number n actually represents the level of the system, the number of energy levels of the system. So if you have a two energy level system, then you will have a 2 by 2 matrix, a Hamiltonian matrix. If you have a three energy level system, then you will have a 3 by 3 energy level system. Okay, so in general, it's an n by n matrix. Okay. So let's go directly to an example. So suppose you have a two-level system, so two energy level system, and the system starts out in this state. So the initial wave function is given. So it's a two-level system, meaning the Hamiltonian is a 2 by 2 matrix, and the eigenfunctions are 1 by 2 matrices. So it has 2 rows and 1 column, since these are vectors. These are Coulomb matrices. So this is the classic problem, right? You are given the initial wave function and you are asked to find the wave function at any time t. So of course you will need our equation for the state. So this is actually what is asked of this problem, the general state, what is the wave function at any time t, and it can be obtained by doing a linear combination of the stationary states. Okay, so in order to solve this, we need to solve first for the eigenfunctions Sn. And this can be solved using the time independence coordinate equation, more specifically the characteristic equation. So H minus En(I). So before you can solve the eigenfunctions or the stationary states, the time independent wave functions Sn, you must first get the energy eigenvalues. So you get the energy eigenvalues. If you know now the eigenvalues, then you can now solve for the energy eigenfunctions. So if you now have solved the energy eigenfunctions, you can now then solve for the linear combination coefficients. This is done by taking the inner product of the wave functions, time-independent wave functions, with the initial wave functions. So depending, since this is a two-level system, you will expect that your energy eigenvalues are 2, E1 and E2. You will expect your eigenfunctions to be also 2, S1 and S2. You will expect your linear combination coefficient to be also 2 values, C1 and C2, since this is only a two-level system. Okay. So let's first start with this equation, the characteristic equation. Okay. So what is now our Hamiltonian? So let's just assume a general Hamiltonian. So it's a 2 by 2 matrix, so it has 4 elements. So since the Hamiltonian is Hermitian, meaning its adjoint is just itself, meaning the transpose conjugate of the matrix must be itself. So you create a matrix like that. So you can actually have a matrix something like this, H, G, G, H. So if you take the adjoint of this, the adjoint means transpose. So you flip along the diagonal and then take the conjugate. So assuming G and H are real numbers, real values, then if you take the transpose and the conjugate, you will still get the same matrix. So that's the definition of a Hermitian matrix. So this will now be our general Hamiltonian. So we will now try to find the energy eigenvalues. So first, solve for the energy eigenvalues. So we do that by solving the characteristic equation. So we have the determinant of H minus En. The ENs are still unknown. The identity matrix I. The determinant must be equal to 0. So we have the Hamiltonian H, G, G, H minus En. The identity matrix again is just a diagonal matrix with 1 as the diagonal elements and 0 off diagonal elements. So the identity matrix is just, in this case, it's a 2 by 2 matrix. So 1, 0, 0, 1. So you multiply En to this and you will get a matrix like this. En, 0, 0, En. Must be equal to 0. So take the subtraction and take the determinant. So you will have H minus En. This will be the first term in the subtraction of these two matrix. The second term will be G minus 0, so G. And you will have G minus 0, so G. Then H minus En. Okay, so it's just very easy to solve for the determinant of a 2 by 2 matrix. You can just use basket method. So multiply this diagonal here, subtract by this diagonal here. So that will give you h minus en squared minus g squared. So this is the determinant of this matrix here. And this must be equal to 0. Okay. So transpose g squared and you will get h minus en equal to squared is equal to g squared. Now, when you take the square root of a number, it's always two values, positive and negative. So take the square root both sides, you will get h minus en is equal to plus and minus g, because it's always two values. So therefore, I can now solve for en. En is actually equal to, say, h transpose that, and you will get a minus plus g. So I actually have two values of en. So I can actually say E1 is h plus g, and I will let E2 as my h minus g. Okay. Actually, the notation used by Griffiths is actually E plus and then E minus, since there are only two. But you can actually make your own notation. By the way, if you make these are these are energy levels. The lower energy level of the two must be at the bottom, and the higher one must be at the top. So in this case, if you use the E minus E plus notation, E minus is definitely lower because it's h minus g, and E plus is definitely higher. So you can think of this, since this is just a two-level system, you can think of E minus as the ground state energy level, and the E plus as the first excited state energy level, and there are only two levels. So you can also let this as your E1 and E2 if you like. So meaning E minus here will be my E1 and E plus here will be my E2. So these are energy levels. The lower one is at the bottom. The higher one, the excited states, are above the ground state, or the lowest energy level. Okay, so it's up to you. But I'm just gonna use E1 and E2. E1 is the ground state energy. E2 is the first excited state energy. So we now have solved the energy eigenvalues. Let's now proceed to solving the eigenfunctions, Sn. So in order to do this, we need to go back to our time independent Schrödinger equation. So we have the Hamiltonian acting on Sn equal to En Sn. So since there are two energy eigenvalues, you must do this twice. I'm just going to solve the first one. So I'm just going to solve H acting on S1 is equal to E1 S1. So I already know E1. E1 is this, H minus G. And I also know the Hamiltonian. My Hamiltonian is just H, G, G, H. So I still don't know what's my S1. So I'm just gonna represent it by just two variables, alpha and beta, since these are still unknown. So these are the components of my S1 eigenfunction vector or eigenvector. So E1 is just H minus G. So S1 is alpha and beta. Okay. So solve this equation. So matrix multiplication. So you have this becomes a 1 coulomb matrix, H alpha plus G beta. That's the first element. And the second element is G alpha plus H beta. And this must be equal to, so you will have H alpha minus G alpha, and then H beta minus G beta. Okay. So what does this imply? You have two column matrices here, and they're both equal, meaning the components must be the same. So this means that H alpha plus G beta is equal to H alpha minus G alpha, or I'm going to cancel H alpha or subtract H alpha both sides of this the two equation that you will generate here, and you will get G beta equal to negative G alpha. So divide both sides by G, and you will get beta is equal to negative alpha. So the second equation is actually unnecessary, not necessary, because you will still get beta is equal to negative alpha, or alpha is equal to negative beta. So we now know that our S1 is alpha is alpha and beta is just negative alpha. So we can actually factor out alpha, and you will get 1, negative 1. So how do you solve for alpha? So in the same way that you solve a normalization constant. So alpha here is actually just a normalization, some normalization constant. So how do you solve for the normalization constant, or alpha here? You dot the vector with its self, and then that product, the vector with itself, must be equal to 1, because so that it will be normalized. It's a unit vector essentially. It's a unit vector essentially. So you take the dot product of this vector with itself, the inner product of this vector with itself. So I'm gonna do this S1, S1. And this should be equal to 1. This is the normalization condition. This is similar to integral of psi m dx. Psi m conjugate. So since this is a bra, it's conjugated. So in this case, since assuming they are real, so I will have S1 is the conjugate of this. So assuming alpha is real, so we'll just get alpha squared, and then the adjoint of this, or transpose conjugate of this, is 1, negative 1, and then 1, negative 1. This must be equal to 1. So you will then have alpha squared. So the result of this multiplication of a row matrix and a column matrix is just a number. So 1 plus negative 1 times negative 1 plus 1, so you have 2. So 2 alpha squared is equal to 1, meaning this implies that alpha is 1 over square root of 2. And you will get now, you have now obtained your S1. S1 is just equal to 1 over square root of 2, and then 1, negative 1. So you do the same for S2. You again start with the Schrödinger equation, but it's now for S2, and then use the second energy eigenvalue, E2, this one, H plus G. You do that, and you will obtain S2, which is just equivalent to 1 over square root of 2, 1, 1. So E1 is the ground state energy, and the state actually is S1, which is, the state here is S1. This is the ground state, S1. And the form of S1 is this one. And the second energy level is E2. And the state there is S2, which is given by this value here. Okay. So we now have obtained the energy eigenvalues, H plus G. So S1, this state of a particle, corresponds to the energy E1 equal to H minus G. And S2 corresponds to an energy of H plus G. So these are now our correspondence. So we now have solved the energy eigenvalues and the energy eigenfunctions. So again, what we are trying to solve is the general state of the system, and it can be obtained as a linear combination of your independent states, time independent states. So e to negative I en t over h bar Sn. So this is just from 1 to 2, since this is just a two-level system. So we already know the ENs, this 2. We already know the SNs, the time-independent wave functions, so this one. So what we are left with the unknown. The last unknown for our problems are the CNs, so C1 and C2. So we can solve C1 and C2, the CNs, by taking the inner product of the eigenfunctions Sn with the initial wave function. So we are actually given the initial wave function here. This is our initial wave function, 1, 0. So for C1, this is just S1 multiplied, or the inner product of S1 with the initial wave function. So S1, so this is the ket version, or sorry, bra version of this ket. So you take the transpose conjugate. So since these are real, so it's just plain conjugation. Sorry, plain transpose. So the transpose of S1 here becomes a bra S1. So of the bra S1 is just 1 over square root of 2. The row matrix becomes, the column matrix becomes a row matrix, 1, negative 1. And the initial wave function is 1, 0. So you have 1 times 1, 1 plus 0, so you have 1. So C1 is actually 1 over square root of 2. You do the same for C2. So S2 acting on, or inner product of S2 and the initial wave function, and you will still get the same result, 1 over square root of 2. So you now know the linear combination coefficients, C1 and C2. You now know the energy levels and the SNs, the time independent wave functions. So you can now write your wave function at any time t. Okay. So the wave function at any time t will now be, so I'm just going to expand this. So you will have C1 e to negative I E1t over h bar S1 plus C2 e to negative I E2t over h bar S2. That one, the expansion of this from n is equal to 1 to 2. So we already know C1, that is 1 over square root of 2. E to negative I, E1 is h minus g. We have h minus g, t. Take note, h here is not a Planck's constant, huh? It's just a number. So please don't cancel it with h bar. And S1 here is 1 over square root of 2, 1, negative 1. So this is our S1. So plus C2, which is also 1 over square root of 2, e to negative I, h plus g, t over h bar, and 1 over square root of 2, 1, 1. So you simplify. So this becomes a column matrix. This is also another column matrix. So the result, the final result is a column matrix. So I'm gonna leave this as an example to you. So you will actually get something like, so this is now the wave function at any time t. So just simplify this one, this matrix. So there will still be a common factor, e to negative I ht over h bar. Please again don't cancel the h bar. And then you will have cosine gt over h bar minus I sine gt over h bar. So this is the wave function now at any time t. So we use the property of cosine here, e to the I theta plus e to the negative I theta over 2, that's cosine theta. And for sine theta, That's actually e to the I theta minus e to the negative I theta over 2I. So we use the property of cosine and sine. So our theta here is actually gt over h bar. So you will notice that at time is equal to 0, this is just e to the 0 or 1. Cosine of 0 is 1. Sine of 0 is 0. So you still achieve the initial wave function. The wave function at time is equal to 0. You will still get that one. You can actually verify the Schrödinger equation of this. So you operate the Hamiltonian on this state, and it must be equal to IH bar partial of this one with respect to t. So you can check the Hamiltonian equation, the time-dependent Schrödinger equation for this general state. So our result is a vector. It's a Coulomb matrix. So let's now have another example. So we are now given the Hamiltonian of a 3-level system. So this is a 3-level system, meaning it's a 3-energy level system. So you will have E1, E2, E3. So E1 is the ground state. We are given the Hamiltonian. So you can check that this is Hermitian by taking the transpose and then conjugate of this, or taking the adjoint transpose conjugate, and you will still get, you should get the same matrix, where A, B, C are all real numbers, so their conjugates are just themselves, and A minus C must not be equal to either plus or minus B. So these are the conditions. So if the system starts out in this state, so take note, this is a 3-level system, meaning your eigenvectors now, or your state vectors, or your wave functions are basically a column matrix with 3 rows, or a 3-by-1 matrix. So the same problem, if the system starts out in this state, what is the state at any time t? So I will no longer be explicitly solving this problem, but again, you will start with the characteristic equation. So to solve for the energy eigenvalues, so H minus En times I, the determinant of this matrix subtraction must be equal to 0. So the identity, since the Hamiltonian now is a 3-by-3 matrix, your identity operator matrix now, it's also a 3-by-3 matrix. So you do that, and you will get 3 energy levels. So you will actually get, if you solve the determinant of this matrix, you will actually get 3 values: C, A minus B, and A plus B. So at this point, we are not sure which of these 3 energy levels is the lowest. So we are not sure who is the ground state, which is the ground state, but that actually doesn't matter right now, because we are only trying to find the wave function or the state at any time t. So we can, for this problem, we will just let C as our E1, A minus B as our E2, and A plus B as our E3. So you then again solve for the Schrödinger time-independent Schrödinger equation. So you will have the Hamiltonian acting on S1 equal to E1 times S1. So the Hamiltonian is given by this. You have A0, B0, C0, B0, A, and we will just have a variable S1. So its components are alpha, beta, gamma. We will try to solve alpha, beta, and gamma. So E1 is C, and then you will get alpha, beta, gamma. So this implies that you have A alpha plus 0 plus B gamma. So you have A alpha plus B gamma. Then you have 0, C beta, 0, C beta plus 0, so C beta. And B alpha plus 0 plus A gamma. So this column matrix is equivalent to C alpha, C beta, C gamma. Okay, so this implies that A alpha plus B gamma is equal to C alpha. So A alpha, I'm just going to transpose this. So you have A alpha minus C alpha, or A minus C alpha, equal to, transpose that, negative B gamma. So this is alpha. So for the middle term, it's just C beta is equal to C beta. You don't have information on that. For the last terms here, you will have, I will transpose this, and it will become A alpha, or I will transpose C so that it will become A alpha minus C alpha, or A minus C alpha is equal to, transpose again, negative B, gamma pala, and then B alpha. So what does this result imply? So from the first, this implies that alpha is actually negative B over A minus C gamma. Now if you use this value here and substitute it here, so you will have A minus C times gamma. Gamma is equal to negative B times alpha, which is that one, negative B gamma over A minus C, and you will get what? You will get A minus C squared over B squared is gamma is equal to gamma. What does this imply? There's a condition here. A minus C is not equal to either plus or minus B. So the numerator here is not equal to the denominator here. So this is not equal to 1. And you have times gamma is equal to gamma. So what must be the value of gamma in order for this equation to be valid? Gamma must be equal to 0. That's the only way for this equation to be valid. So you will get gamma to equal to 0, meaning if gamma is equal to 0, alpha is also equal to 0, and your equation or your matrix S1 matrix will just be 0, beta, 0. So your S1 matrix or vector will just be 0, beta, 0. 0, beta, 0. So you have beta 0, 1, 0. And obviously, if you normalize this, take the inner product of S1 with a bra S1 and a ket S1 and equate it to 1, normalization condition. So you will get beta is equal to 1. So you will actually get S1 to be 0, 1, 0. You repeat the same steps to solve for S2 corresponding to this energy level here, and you will get 1 over square root of 2, 1, 0, negative 1, and S3 corresponding to this energy level here is 1 over square root of 2, 1, 0, 1. So you now know the energy levels, E1, E2, E3. You now know the eigenfunction, S1, S2, S3. What's left to solve are the linear combination coefficients, C1, C2, and C3. So to solve for the linear combination coefficients, you take the inner products of your time-independent wave functions and multiply it with the initial wave function. If you will notice here, our initial wave function is actually S1, 0, 1, 0. So recall, at time is equal to 0, the time-independent state becomes summation of n Cn Sn. So what you're trying to do here with the linear combination coefficients is you are actually trying to write the initial wave functions in terms of the given, in terms of the eigenfunctions or the time-independent wave functions or the time-independent states. But since this is already equal to S1, that is 0, 1, 0, then if you take C1 and then S1, S0, that's actually basically just S1 with itself, the inner product of S1 itself, and that will give you 1. If you will solve for C2, so you have S2 and then the initial wave function, which is just essentially S1. Take note that these three eigenvectors are orthogonal to each other, meaning the inner product, just like x hat, y hat, and z hat, or I hat, j hat, and k hat, those are orthogonal with each other. So I dot j is 0. So meaning S1 dot S2 is also 0. S2 dot S3 is also 0. Since our initial wave function is just basically S1, so S2 dot S1, that will give you 0. And C3 will also result in 0. So meaning only one term in the summation will survive. So the wave function now at any time t will then be only C1. So you will get C1, which is just equal to 1, C1 e to negative I E1t over h bar S1. Since the second term and the third term in the summation are all, the C2 and C3 is equal to 0, then that makes the second and last term, the third terms, be equal to 0. So in this case, you will just have e to the negative I E1t, where E1 is just C, sorry. So I Ct over h bar, and then S1 is 0, 1, 0. So this is our wave function at any time t. So you can verify that it will satisfy the initial condition at time is equal to 0. It's 0, 1, 0, our given initial wave function. Okay, so basically that is the process. It's very repetitive. You solve the characteristic equation, solve for the energy eigenvalues, then one by one you solve for the corresponding energy eigenfunctions for every energy eigenvalue. And so once you have solved that, solve for the linear combination coefficients, and then expand the summation equation and simplify. And basically that's it. Okay, there's a last question here. So there's a last question here. You're actually asked to find the probability for each energy level. So the probability for each energy level in this case is actually just the absolute value of Cn squared. So since C1 is equal to 1 and C2 and C3 are all 0, meaning there is a probability of 1 for the energy E1. So for this specific case where the system starts out in this state, it actually starts out in S1, then the probability of E1, which is equal to C, the probability of this energy level to occur when you measure the energy of this particle is 1 or 100%. The rest, the probability of E2 and E3, so A minus B, A plus B, the probability of E2 and E3 are all 0. So when you measure the energy of this particle, which is in this state, then you will only get one value, and that is E1 is equal to C, provided it starts at this initial wave function. Of course, you will have a different result. You will have a different state if you have a different initial wave function, given the same Hamiltonian. That one. Okay, so basically that is it for this lesson, and essentially that is it for this chapter. So in this chapter, we have generalized the concepts in quantum mechanics. We have generalized the statistical interpretation, the uncertainty principle, and the concept of the wave function, which is just essentially a vector that lives out there in Hilbert space, independent of any coordinate system. So I will see you again in the next chapter.